Okay, looks like we're up here. Um, this is unfortunately the next video I had to edit from a previous recorded video, last year's chapter 23.
Polonium-239 with a neutron. We hit it with a neutron. The resulting nuclei are so unstable that they break apart into two smaller daughter nuclei, releasing more high-speed neutrons. Okay, and the mnemonic for this is fission is division. Okay, and this brings us to, this is the fission equation for bombarding a uranium-235 nucleus. We hit it with a neutron, okay, and then it hits U-235 nucleus, turns it into a U-236 nucleus, but just for a little bit, because there's a lot of energy there, and it's not very stable at all. So then it turns into its daughter nuclei, which would be krypton and barium. Now if you look again, krypton is sitting here with 91 nucleons, and barium is sitting there with 142 nucleons, and so that's a total of 233 nucleons. Well, we have 236 to account for. Now, 36 and 56, that's 92, so we've got all of our protons, but we're still missing 3 nucleons that are not protons, and so they must be neutrons. And so they actually get released individually with a little bit of energy. Okay, this then creates a chain reaction, because the fissioning process starts with one neutron causing one atom to break apart. And when it splits, it gives these 3 neutrons, and they send those 3 neutrons to go hit 3 more uraniums. Okay, which is going to split and give off, each one of those is going to split and give off 3 more neutrons, which is going to go hit 3 more uraniums, so now we're up to 9 nuclei. And then each one of those 9 gives off 3 to hit 3 more nuclei, so we're up to 27. And so on, 81, 241, 2723. Those aren't right. That should be, oh, I should correct this. Okay, those numbers are better. So, it's 1 to 3 to 9, 27 to 81, and then those put off 3 to make 243, and those put off 3 to make 729, and so on and so on, with trillions and trillions of reactions in less than a second. Okay, so go see figure 2510. Okay, because that's going to show you what that looks like. Now, when atoms split, a tiny amount of mass is destroyed. It's about 0.1%. However, that gets converted into energy based on E equals mc squared. Yes, that E equals mc squared. Einstein's mass to energy equality. So E equals energy created, measured in joules. M is the mass defect, or it's the mass lost, measured in kilograms. Okay, and C is the speed of light, which is about 3 times 10 to the 8th meters per second. Well, if you square C, that makes 10 to the 16th, and that becomes a really big number really fast. So even if the amount of mass is really small, the energy is huge. So it brings us to, like we said, C squared is a really big constant, 9 times 10 to the 16th meters squared per second squared. You're not going to be expected to know how much energy is released, because you don't even know what the energy is, so I'm not going to require that of you guys. However, recognize this, that an average atomic bomb might have about a kilogram of U-235 in it. Just a kilogram, about 2.5 pounds, or 2.25 pounds. When 1 gram of U-235 is destroyed, it's the size of a BB, and so this loses about 1 gram of U-235 and converted into energy. Okay, if the 1 kilogram fission bomb releases the same amount of energy as 20 kilotons of dynamite. 20,000 tons of dynamite. Ridiculous amount of energy, all concentrated in one place. Okay, now fission is also used in nuclear reactors, and you need to know this. Okay, there are some advantages to nuclear energy. Okay, there's lots of energy produced frequently, with minimal effects on the environment. Okay, it is usually reliable. It is usually very reliable. Okay, and it doesn't cause air or water pollution like the use of fossil fuels. And there are many American-designed safeguards. However, some of them you just can't control for, like, say, having a tsunami and an earthquake happen at the same time. Nuclear reactors, nothing is designed to withstand that. Then there are some disadvantages also. There's a limited amount of fuel, and the plutonium U-239 breeder reactors are not as safe as U-235. The products of the fission reaction have long half-lives, and they're very radioactive. And so they have to be stored, so we produce a lot of it, okay, and they have long half-lives, so we have to store them for a very long time. And storage for something like that is very expensive. And nuclear waste could be stolen and converted into plutonium-based bombs, which also is a bad thing. Okay, so the waste places are heavily guarded. Okay, which brings us to the answer, which is nuclear fusion. Fusion is the bringing together, or the combining of small nuclei to produce a larger one. For example, two hydrogen isotopes, hydrogen-2 and hydrogen-3, also known as deuterium and tritium. Okay, they will combine to make helium, which is utterly harmless. You all know that because you can breathe it and your voice starts sounding like this. Okay, and it gives us the neutron and some energy. Matter is destroyed, just like in fission, and converted into energy from equals mc squared. However, fusion is more efficient than fission because 0.5% is converted into energy, as opposed to 0.1%. So it's 5 times as efficient as fission. Fusion is also what powers the sun. We have a constant fusion reaction lighting our sky, providing 100% of our energy. Of all the energy that we produce on the planet, all of it comes from the sun. You can trace all of it back to the sun. From wind energy, solar energy, to nuclear energy, all of it can be traced back to stars. And fusion reactions are the answer to our energy demands for the future. There really is no other option. We have to go through fusion because we have a limitless supply of the material needed to do it, to do fusion, and the amount of energy we get out of it would make the economic impact minuscule. Okay, which brings us to nuclear bombs. Atomic bombs are fission bombs using U-235 and plutonium-239. So the isotopes of uranium and plutonium. In order to make an atomic bomb, we had the Manhattan Project, which was a top-secret government project to design and build the atomic bomb under the football field at the University of Chicago. Okay, which led to the Trinity Project, in which three bombs were made. There was a demonstration in Alamogordo, New Mexico, and then the 2 that were dropped. The other 2 that were actually dropped in anger, and they were the only 2 that have ever been dropped as attacking weapons against an opposing force. The atomic bombs reach temperatures above 10 million degrees Celsius, and they release all forms of radiation, and they are a fission reaction that has gone horribly out of control. Now, we, of course, like bigger and better bombs, and so we made fusion bombs, which are called thermonuclear bombs, or hydrogen bombs. They use an atomic bomb, a fission reaction, to detonate the fusion bomb. That's how they get all the energy to make the fusion start. In 1951, we dropped the first hydrogen bomb. It was detonated in the South Pacific island of Bikini Atoll. Now, rumor has it that the Bikini Atoll was not actually an atoll until they dropped the bomb on it, and then it became an atoll. Someday I'll show you a picture when I get back to class. Some scientists thought it might ionize the atmosphere, which would, completely tear all of the compounds and all of the gases in the atmosphere and turn them into ions. Fortunately, that didn't happen. It was 1,000 times more powerful than the Hiroshima bomb, and it reached 100 million degrees Celsius. put these suckers on top of ICBMs, which are called intercontinental ballistic missiles, and most of our nuclear warheads are hydrogen bombs, and the warheads on these things contain multiple bombs. So you launch one, you set it and forget it. You launch it, and it will attack 10 different targets. So just let them go from space, and they'll fly down, and they'll attack 10 different targets on their own. Okay, which brings us to radiation in your life. We have 3 basic devices for detecting radiation. There's a Geiger counter, there's a scintillation counter, and film badges. This is what a film badge looks like. Right here. Okay, so if you look at the film badge, there's a monitoring film in here, and look at the kind of filter that it has. It has an open filter, it has an aluminum filter, a copper filter, a plastic filter. Okay, what do you think is going to show through the open window? Well, it's the things that don't have a filter, and so that's going to be the alpha particles are going to show up through here. Okay, but if you have the plastic filter, well, that's going to see if you have some high energy alphas as opposed to just betas, but it's going to get stopped by the aluminum filter. Betas will get stopped by the aluminum filter. And so if you have markings here on the copper, now you're talking about neutrons and gamma radiation, and that's bad. If you've got exposure up there, now you really felt it. So the monitoring film, which goes all the way back to Becquerel, all the way at the beginning, they put photographic film there, so that when it gets detected and you enter radiation, you know exactly which type you have. Okay. And then finally, we actually use radiation. We use radioisotopes in medicine to detect various disorders. We detect it in the thyroid. It can also detect tumors and liver disorders in nuclear medicine. And people take radiation therapy and radioactive isotopes to go attack cancers in the body. And that's it. And I know that was a long one, but that's the entirety of Chapter 25. And fill out your notes, and I will see you on Monday if we actually get through all of it. Peace out. Word to your mother.